So in this last video, we're going to talk about the difference between an ideal gas and a real gas. Okay, so all the problems that you've done in chapter 18 have not taken into account what type of gas it is. Every single equation you use, Charles' law, V1 over T1 is equal to V2 over T2. Boyle's law, P1 V1 is equal to P2 over V2. The combined gas law. None of these equations care what type of gas it is, whether it's hydrogen, oxygen, nitrogen, it doesn't matter, okay? And the reason why it doesn't matter is because we make some assumptions that aren't true. So with an ideal gas, there are three assumptions we make. One, that they are point masses. Okay, point masses are gases that have volume, that have mass, but no volume. Okay? In other words, the gas particles do not take up space. The second point is that the gases have random motion. That there is no attractive forces between gas particles. And then the third point of ideal gas theory is that you have perfect elastic collisions. So a perfect elastic collision is a collision where no energy is lost in the collision, usually in the form of heat. Okay, so numbers 2 and 3 are a little bit more self-explanatory, but I want to explain a point mass. So if you have a container of gas, the gas particles themselves take up space. And so if you had a piston and you wanted to compress the gas, eventually you would not be able to compress the gas anymore because the gas particles themselves take up space. Now, what we're saying is, let's pretend that's not true. Let's pretend that the gas particles actually don't take up space. So in other words, let's say that I'm having trouble advancing to the next page here. Bless it. There we go. Now I got it to go. So, like I said, in reality, sorry that my computer glitched there, you can't compress the gas all the way down, okay? Because the gas is made of something. So this can't happen. What we're saying is, let's pretend, however, that the gas particles actually don't take up any volume. Well, if the gas particles don't take up any volume, then you could, in theory, compress the gas down to a volume of 0. Up here, you cannot compress the gas to a volume of 0. It's impossible, because the gas particles take up space themselves. So this is what we mean by a point mass, meaning that the thing has mass, but absolutely no volume. So now, why would we do something like that? Why would we make an assumption that obviously is not correct? And the reason is it makes our calculations much more simple, okay? And, you know, I kind of use this as an analogy. We say, what's the difference between a real gas and an ideal gas? A real gas and an ideal gas, the difference is the same thing between what we have in our heads as our ideal spouse or partner and our real spouse and real partner. We all have this ideal of this person who is caring and kind all the time, and they've got blonde hair, blue eyes, and they're super smart and funny. Well, that's the ideal, okay? The ideal doesn't exist, okay? In reality, you have a person that, you know, their hair gets gray, they get wrinkles, they get crabby sometimes they get upset, some of the times they're happy. So you have your ideal in your head, but then there's reality, okay? So we have this ideal of how we want a gas to act, but in reality, a gas does not act that way. In reality, a real gas is a gas that has mass and volume, and that the motion is not random, in other words, the gas particles attract each other. So if one gas particle is near another gas particle, they don't just move randomly. There's a little bit of attraction between these two gas particles. And so they'll come closer to one another. Okay? So the motion is not random. And then the third thing is the collisions are not elastic, or we would say inelastic, meaning that when two things collide, heat is lost. I should say energy is lost in the form of heat. Okay? So the name of the chorus that I sing in is called the Capital Chordsman. So if you're actually watching this video, you'll know. And that'll be a question on one of the quizzes just to make sure that you guys are actually watching this video. So be sure to write that down so you get that question right. Otherwise, I'll know that you're just skipping straight to the quizzes, which I told you not to do. Okay? So why do we have this distinction between ideal gases and real gases? Wouldn't it make more sense to deal with reality as opposed to living in this ideal fantasy world of how gases react? Well, here's the reason why. This is the real gas equation. Okay? A is the attractive force between gases. Okay? Just like people, some gases are more attractive than others. Some gases are really attractive and the particles stick together. B is the size of the gas. Some gases are bigger than others. Argon gas is much bigger than helium gas, and so you have to take that into account. The other variables are the same. P is pressure, V is volume, N is the number of moles, T is temperature, R is what's called the universal gas constant. I think what I'm going to do is I'll make a video for those who are interested to see where the universal gas constant comes from. But the universal gas constant is 8.31 liters kPa over moles times Kelvin. It can also be reported in ATMs, 0.821 liters times ATM mole Kelvin. So those are the two values for R. Now, the ideal gas equation is just this, P times V equals nRT. So if you pretend that gases do not have, if you pretend that gases do not have attractive forces, and if you pretend that gases are all the same size and are point masses, well then your equation simplifies to this. Now which equation would you rather use? This one, PV equals nRT, or would you rather use this one? Well, that's why we use the ideal gas equation. And here's the beauty of it. It doesn't matter which equation you'll use, your answers will come out to be almost identical. So if you use this equation and you use this equation, your answers will be almost identical. The only time you have to use the real gas equation is when you are under extremely high pressure. Then you must use the real gas equation. Okay? I will make an optional video about how the ideal gas constant comes to be, and I'll show you some graphs, but this is just enough to give you an understanding about what's the difference between real and ideal.